All right, so if we're starting here, let's talk real briefly about what we did yesterday. So yesterday we did the experiment, right? We're flipping the coins. We cataloged. Did it come up 0, 1, 2, 3, or 4 heads? And we came up with a graph that had a shape that went something like this, or something like the illustration over there on the board, okay? How would this graph change? Hopefully your graph looked good. If we just switched this to we were cataloging the tails instead of the heads, that graph would have actually just reflected back the other direction. So it wouldn't have made that much difference in what we were looking at. And then how would this graph change if we decided to do 6 flips instead of 4? We would have had the center on 3, but it would have still been rising up, coming back down. Much more difficult to get all 6 coin flips on heads or all 6 coin flips on tails. All right? So let's go to the notes further on leading into today. The first thing you have to do is you're going to take a look at this video about the Galton board. Because I'm recording this right now, we're actually going to come back to that look at the Galton board. But what the Galton board is going to do is it flips over and it has a whole bunch of pegs and it allows the balls to come bouncing down and it ends up in a normal distribution almost every single time. So this is just something that kind of relates back to what we have in real life. If we have a whole bunch of kind of 50-50 decisions and we have a long period of time or a whole bunch of tests, bless you, to get through on that. So this is the first thing that you really need to make sure that you draw in those notes for today. This is the normal distribution. This is what we are looking at. It's also known as a bell curve. And statistically, this is what should happen over a longer period of time. Stuff that is much less likely is out here on the outer edges, and stuff that is more likely, that is happening more often, is happening right here. And the focus of this bell curve, instead of being the mode or the median, is always going to be the mean. When we calculate standard deviation, as we did the other day, we calculate standard deviation from the mean. So we really need it to be one of these bell curves in order for us to do that. If we have information that is taking us skew right, skew left, that's going to affect how the standard deviation is calculated and what it's going to end up looking like. Okay? So, standard deviation on the standard distribution or standard deviation on the normal distribution. We talked about standard deviation. We talked a little bit about what that meant when we did the delivery problem. This is very, very important. You need this information for the upcoming exam. So, around 68% of the data is within one standard deviation in each direction. Okay? When they say within one standard deviation, they mean one above or one below. The easiest thing for me to think of in this case is usually IQ. I think I may have talked about this to some of the classes the other day. The mean, the average IQ for someone, at least as I understand it, is 100. So that would be right here in the middle. And the standard deviation on IQ points is 15 points. So if you are all the way up to 115 or all the way down to 85, you are within one standard deviation. So this is all the normal intelligence people, according to the IQ test at least, and that's 68% of the population. Okay? Now, if this is 68, let's do some math today. That means that everything from the mean up one standard deviation is what percent? 34. And everything from the mean down one standard deviation is the other 34, right? Okay, so make sure you know all of this. List this. This whole part within one standard deviation is 68. Up one standard deviation is 34, down one standard deviation is 34. Okay, half on each side. This should all come out really even. All right? The next standard deviation, within 2 standard deviations, boop, boop, that is 95%. Okay? That's a big deal. 95% of the entire population falls within 2 standard deviations of the mean. If you think of this school, and we have like 2,000 people, all right? This would be 1,900 people in the school would fall within this range, within 2 standard deviations. If we're talking about almost anything, height, weight, IQ, whatever it is, we could put it all together, we can find the mean, we can figure out what the standard deviation is gonna be, and 95% of the school is gonna be within 2 standard deviations, okay? Now, more math, right? What's 95 minus 68? 95 minus 68.
27.
Okay, so we have 27% that we have added in. All right, what's 27 divided by 2? 13.5. So this right here, from 1 standard deviation to 2 standard deviations, this little part right here is 13.5%, and this little part over here is 13.5%. Very important. You need to make sure that you know that. Write that down. Okay? So the middle part is 68%. So it's 34 and 34. This larger part right here to 2 standard deviations, that's 95. But it includes that 68 that we already have. So 13.5 over here, 13.5 over here. And that takes us up to 95%. So then, like we have average, we have above average, we have below average, that's 95%. Then we get into exceptional, okay? Within 3 standard deviations is 99.7, okay? 99.7. So if we have 99.7 and we subtract 95 from that, we get
2.7. Wait, what did you say? 96? Oh, you said
90.
Oh, 4.7.
Yeah. So we have 4.7% that got added in. So we're talking exceptionally high, exceptionally low, and it's only 4.7% of the population. All right? And again, we need both halves of this. So 4.7 divided by 2 is going to give us 2.35. Okay? So this right here, from the +2 standard deviations to +3 standard deviations, is 2.35%. And down here, same thing, 2.35%. The beauty part is, if you understand this, this will carry you a good chunk of the way through AP statistics. Because most of what they do, or at least for a while, a unit or two, is centered around figuring out how we fall in a normal distribution and where everything is going to be. So this is also our upcoming test. Okay? So make sure you have this image. Make sure you know how much every little change in both directions is worth. You do, I think, have access to these notes. I think I put it on today's. If I didn't put it on today's Schoology, it is still on yesterday's. Okay? It's just one big set of notes, day 1, day 2 on there. Okay. So, interpreting graphs. This is something that is real. This was a study that they had, and it represents birth weights in the United Kingdom. And because it's in the United Kingdom, it's in kilograms. They superimposed over the histogram the normal distribution. So you can see, like there's a little edge right here. There's some higher peaks up here. There's some stuff outside of what they usually measure over here. It's not perfect, but it does fit pretty well. And if we understand that about the normal distribution, we can use that to predict what's going to happen. So if there are 3,226, we find the mean. The mean is 3.39. The standard deviation is 0.55, just a little over half a kilogram, okay? Within one standard deviation, what should we see? What percent should be within one standard deviation? Not just up, but also down. 68%, okay? So how would we find how many babies we would expect to see within one standard deviation? What's 68% of 3,226? You don't have to tell me, but how would we find that? Anybody remember percentages?
By dividing it by 101 by 68.
Okay, or we can do it in one step. If we take 3,226 and multiply by 0.68, that'll tell us that 68% of that, that's how many we should expect to find within that, okay? 2 or 3 standard deviations, again, 3,226 times 0.95, that would be within 2 standard deviations. 3,226 multiplied by 0.997, that would give us everything within 3 standard deviations. Just a quick question, let's see if we're awake this morning. Why do we see some down over here above what we would see for exceptional, but we don't see any over here?
Because there's smaller people than there are bigger people.
These are babies, right? You're not wrong, okay? These are babies, yes? So why would we have these down here? What kind of babies are very, very small? Premature, right? You do have premature babies every once in a while, and we have the technology in the healthcare now to help keep those babies alive, keep them healthy, make it to where they're gonna be okay. So we get some of these down here on the very, very small end, and they're gonna be okay. Why wouldn't we have them over here on the large end?
C-section.
Yeah, if that baby is that big, the doctors are gonna take it early, they're gonna take it by C-section. So it's actually gonna be weighing in somewhere over here instead of you're gonna have this gigantic, huge baby, okay? Okay, one more thing to add in. This balance of having the 68%, 95%, 99.7% is usually referred to as the empirical rule. So if you see anything on there about empirical rule, this is what they're talking about. In the normal distribution, everything within one standard deviation is gonna be 68%. Everything within 2 standard deviations is gonna be 95%. Everything within 3 standard deviations, 99.7%. And they use that to predict the likelihood of something happening. Here is the most statistically likely thing, and here we go. So that's how we probably could have predicted how many coin flips are gonna come up for any of these like this. Yes? Do I have a sharpener? Yes. Have a piranha. And good news. That's it for the notes today. For this class, we're actually going to go back. We'll watch that YouTube video with the sound plugged in. But for those of you on the recording, if you have questions, make sure to save those for when I come back.